Hi, and welcome to Chapter 5. In Chapter 5, we are going to discuss digital encoding and transmission. How does the data get from one location on your computer? How does it get cut up and turned into encoded to turn into bits? And how does it get transmitted across the network? Let's get started. So quickly glancing at our roadmap, we're at the end of our chapter on media. So again, this was covering the different ways that we transmit data. We can use our copper, our fiber optic, or wireless. So now we're going to discuss how the data starts moving along and getting transmitted before we move on to operating systems next time. So first things first, let's discuss our data signals and our encoding. When we talk about encoding, that means converting the data from whatever data it's in into a digital pattern so that the media can actually send it. So in an electrical signal, we are going to be sending a certain amount of electricity, and it's going to be going in an on-off type situation. So we can go either what we call unipolar, singular polar, which goes from a 0 to a 5-volt range, 0 being off, 5 being on. So if we wanted to send a 1 or an on, we would send a 5-volt pulse. If we wanted to send a 0, we would send a 0 pulse or nothing. So you could count the ones and the zeros as you go along for each of the pulses. You can also have what we call a bipolar digital signal, which is from a -5 to a +5, and a -5 to a +5, and it can go back and forth in this direction. So what we're going to do, if you have ever converted any type of a decimal number into a binary, we are converting into bits. We're converting into on and offs, yes or no's, on 0 or 5-volt, -5, +5. So those are going to be our data, and all data in a computer is represented by those pulses, by those bits. When we want to transmit them, we convert them from zeros and ones on your computer into these digital signals, which we can then send across our media. So whether it's our copper, our fiber optic, or our wireless, we can send those across the media as a series of signals, digital signals. When we talk about those signals, we refer to the time period, which is the rate of recurrence of expected change. So I am expecting to have a change in signal every blank seconds, every blank milliseconds. What is the reoccurrence that I expect to change in digital signal? This isn't the frequency or the cycle like we did in light waves. This is actually how quickly do I expect it to go, either 1 0 0 1 0 1 1 0. Each time would be a different signal, and so we call that our time period. How far is that time period? There are two different ways of encoding. The Manchester encoding is a special type of encoding that is going to do the change in the charge in the middle of the time period. So if we break out our signal into different time periods, normally when we encode, we would put the change in signal at the beginning of the time period, and then we would wait, and then we would change our signal again at the next time period. So if we did these in seconds, just to make them make more sense, obviously it's much faster than that. But if we did them in seconds, at second 0, you could put in a 0. At second 1, you could put in a 1. Second 2, you would put in another 1. Second 3, you'd put in another 1. Second 4, you'd put in a 0. So each of the different signals would have another value assigned to that specific time period. With Manchester encoding, we split it in the middle. We actually change in the middle of the time period. So instead of it being at second 0, second 1, second 2, we actually change at second 0.5, at second 1.5, and at second 2.5. As opposed to being at the beginning or the end of that time period, we put it right in the middle of it. And that's just a different way of encoding. So you can choose to have Manchester encoding or regular encoding for the purposes of when do you change your signal. That time period, again, I'm using seconds as an example, not because we actually do these in seconds. We do them in milliseconds. We do them very, very fast. We also have the option of synchronous or asynchronous transmissions. Whether or not the reference and the data signal are synced together and working together at the same time. So those would be synchronous. If it was asynchronous, there is no reference signal. We're just sending the digital signal. And we'll talk about what that reference signal means in a few more slides. But that reference signal and the digital signal can be together and they are synced together. That would be synchronous. Or the digital signal gets sent by itself. asynchronous with no reference signal to be able to come back and say, did you receive it? Is there back and forth synchronous? Is it important that we talk back and forth, or is it just a one direction asynchronous? I'm sending you data as a digital signal and I don't really care if you received it as a reference. So we keep that. So a couple of things in this slide individually I want you to keep track of is your unipolar versus bipolar. So one direction, one pole, 0 to 5, or bipole, -5 to +5, -5 to +5. And the 0 is also an option in there, but generally we can go straight from -5 up to +5. We can go from 0 to 5 to -5 to 5 to -5 to 0 and change around those. And that just allows us to encode our data just a little bit different. And then of course your Manchester encoding, where we split it in the middle as opposed to splitting it on the ends. Make sure that you recognize the acronym NIC. You're going to see it a lot. That's your network interface card. That's the thing that makes sure that you can connect to your interface, that you can connect to your network. So the thing that your Cat5 would be plugged into, or the thing that's attaching to your wireless router. We're going to be using network cards a lot just to keep track of that idea of, obviously, can't get on the network without a network card. All right, so we have this data. We have this series of bits, ones and zeros. Just like the example here, it literally is ones and zeros. That's what we look at as our data. When we take our data, we break it into segments. So you can start with your raw data. Starting with raw data, which is just a series of ones and zeros. 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 1, 1, 0. Okay, cool. That's our data. When we take our data, pieces of the data that have information in them can be broken into segments that are going to be used for reassembly. We can call these packets. So you can start with raw data, then you end up with segments, and then we're going to use those in our packets to be able to reassemble them correctly. We're going to talk about how data gets transmitted across, but at the other side, you get a series of frames, which can be broken down into packets, which can be broken down into segments, which can be broken down into raw data. So from that raw data, we are then going to be able to take that. So I'm going to walk you through how things get broken up, sent onto the media, sent across, and then received on the other side. So starting with your raw data, whatever it is you want to send, first we break it into segments, little boxes. Cool. Those segments can have what's called a parity check. And the parity check verifies whether the integrity of the information is correct. Cool thing with ones and zeros. If you add up all of your ones and zeros, you will end up with a binary number of either 1 or 0. So if I add up, for those of you that understand binary, 1, 0, 0, 1, 0, 1, 0, I have 3 ones. Mod 2, what's the remainder when you divide it by 2? And the answer is 1. So my parity bit for this 8 bits, or 7 bits, is going to be 1, because I added them all up and I found out the remainder, and it was 1. For the second piece of data, 1, 0, 0, 0, 1, 0, there are 2 ones. Well, 2, mod 2, gives me a remainder of 0, divided by 0, or divided by 2. So its parity bit is 0. If a singular bit of data gets corrupted in the middle of all of this, when it gets transmitted over there, and I tell you my parity bit is 1, and you add up all my ones and zeros, and you end up with something that has a parity bit of 0, you know you lost data. This is just an easy way of verifying the integrity that is really simple and easy to do without a huge amount of data. Literally, it's a singular bit that says when you added up all of these bits, you came up with a 1, you came up with a 0. If it was 1, 1, 1, 1, 1, 1, 1, 7 ones, 7 divided by 2 is going to have a remainder of 1. So its parity bit would be 1. So I hope you understand how you can get the parity bit. It's either an odd or an even parity that says whether or not the number of bits that I have is an odd number or an even number. And that's useful in checking your integrity. If your parity bit is off, then you know that there's something wrong. There is also a concept called a cyclic redundancy check, or a CRC. You are going to memorize this acronym as well, because you're going to think of it every time you think of something breaking, something erroring. It's very similar to a parity check, but instead of it just being the count of the bits mod 2, it's going to be based on an algorithm that actually checks the integrity of the data. So you can have a cyclic redundancy check, a CRC, that is going to check the integrity the same way that a parity bit does. You can choose the parity bit. It uses up less space and it doesn't involve as much effort. Or you can use the CRC, and most things now are going to use that CRC because it's just a little bit more effective at recognizing integrity. If you could imagine with your parity bit, if you had 2 bits that were off, they were supposed to be 1s and they're actually 0s, your parity bit is still going to come back correct because you went through 2 values. So the CRC is more efficient and more effective at actually identifying integrity. Whereas the parity bit, it's great if you have no other option, but we prefer to use the CRC. Okay, so we break our raw data into segments. Each of those segments is separated into raw data and a network header to create what are called packets. Raw data, segments, packets. So a packet has a network header. We're going to be discussing our frames and our frame headers on the next slide to describe those a little bit better for you. Actually, it's not the next slide. It's about 4 slides in. But we'll get into what is included in that network header and then, of course, the next level down. We then break that again, that raw data segments, packets have a network header and a raw data. Frames have a frame, a network header, and a raw data. So those are packaged into a frame and built into those frames. If you remember back to our OSI model when we talked about the data link section and we had the LLC and we had the MAC, the 2 different layers that went along with the data link. The LLC layer did framing. It put things into frames. So this is the frames that we're talking about. This is the layer that happens there where the LLC section is going to frame our data. It's going to frame our packets so that they can be converted. Once you have your frame, and again, we will discuss what frames look like in just a minute, your frame with your network header and your raw data, that is converted down into binary. Again, 1s and 0s. Yes, I know your raw data is also binary, but that's okay. We're going to take the whole thing. We've got our raw data, which is binary, our network header, which is converted into binary, and our frame converted into binary to create a very long binary code. That binary is then converted into digital signals. On, off, 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 on, off, on, off. So we can say 1, 1, 0, 1, 1, 1, 0, 1, 0, 1, 1. And you can see how that digital signal can relate back to what is the binary code for what we're talking about. In this case, we can call it encapsulation or segmentation, which is the breaking up the segments to include the data on the source, the designation, the end of the segment, and the size of the segment. And these go into what I called the network header and the frame. The network header is going to have your source and destination address. This is the part of like a letter that has an envelope and it's got the source and where did it come from, the to address and the from address. That's your network header. We need to know what the addresses are because we need to know where we're going to send it. So that's kind of useful. Inside of our frame, we include different things based on the protocol for that frame. We'll talk about the different protocols that we're going to use and different frames for each of those protocols. Each protocol, TCP, UDP, are going to use different frame formats, and we're going to see what those look like in a little bit. Okay, so there are 2 different types of communication that we use for our data: connection-oriented or connection-less. Connection-oriented needs a reliable connection. I'm going to call you, think of a phone call. I'm going to call you and we establish a session. With that session, I can send data across and get back results saying, you got this, you got the data, did you get it? Did you get it? Are we good? So verification of your packet delivery and this circuit of, I'm going to send you some data, you're going to say you got it. I'm going to send you some data, you're going to say you got it. These are sessions, and the connection-oriented establishes that session. We use the protocol Session Initiation Protocol to initialize the session. That makes sense. Session initiation initializes session. It's shortened into SIP. Again, every time you see a P, think the word protocol and then try to figure out what the other 2 letters are. In this case, it's session initiation. We are initializing our session. So when you do a connection-oriented protocol, you are going to initialize your session with an SIP, and then you are going to do an RTP or a real-time transport protocol. We are going to send data and you're going to respond back with your session, yes, I got it, respond, and so on and so forth. TCP is a connection-oriented protocol. So remembering that TCP is connection-oriented, this is going to be your FTP, your HTTP, and your SMTP. These are all transfer protocols that you are going to be using, and they are all connection protocols. So your file transfer, your hypertext transfer, your SMTP for your simple mail. These are all different types of TCP based. Yes, everybody refers to TCP IP in one phrase, like they're the same thing. They're not. TCP is a connection-oriented protocol, and we create a session and we do reliable transmissions. I know if you got it or not. There's a verification of data. That's the stuff over on the left. Over on your right is your connectionless. This does not make a session. This simply sends information out, and it doesn't care if you got it or not. This is completely unreliable, which is another word we use for it, in the sense that I don't know anything on whether or not you got my data. You don't send me back anything. We don't have that reliability that you would have with a session. So connectionless, there is no session created. The computers do not interact, and they honestly know nothing about each other. Think of this as video. If you are sending something from your broadcast location to send out, it's not like every single computer is responding back, yes, I got the data. They don't care. You're sending video. So your television station, your radio station, these kind of things. The packets are all sent independently. So when we do those packets, they are not sent on a singular session, creating a closed loop or a virtual circuit, however you want to visualize that in your head. With a session, you can think of it as all the packets follow the same direction. They follow the same loop. It's kind of like if you were doing a motorcade of 7 cars all going together and they're all taking the same route and they're all following each other. With connectionless, it's just 4 cars that you say, go to this address, and they could go this way or that way. They could go north or south and eventually end up at the same address. So connectionless, everybody kind of goes their own route and end up on the other side. Again, this is why video is usually buffered, because you're not entirely sure which packet's arriving first. So we use this a lot for video, where honestly, missing data isn't really going to be noticed because the amount of data that's encoded in each packet is small. And so if you are missing 5% of your video, you may not actually see it because it's going to be interspersed. It's not 5% altogether. It's little bits here and there, and you may not even notice that it's missing. Connectionless is going to use either your IP, your Internet Protocol, or your UDP. Okay, so IP or UDP, those are connectionless. There's this great joke on, I'm going to send you a mess, or I'm going to tell you a joke in UDP, but you may not get it. That's because UDP is connectionless. There's no verification that you ever got it. UDP is connectionless as opposed to TCP, which is connection-oriented. So those are 2 things to keep track of. Which one's connection-oriented, which one's connection-less. Try to remember, if I asked you right now which protocol is connection-oriented, you should be able to say TCP and anything TCP-based, FTP, SMTP, HTTP. What is connectionless? IP or UDP. Okay, so these are your different protocols that you're going to reference, connection-oriented or connection-less. So when I said that the data is sent across the internet from point A to point B, there are 2 different ways that you can send that data. Again, if we had the entire data following a singular connection, we would have it like a motorcade. In this example, it would be all the data following the same route. This would be your DSL, your ISDN, your ATM, asynchronous transfer mode, or your T1 dedicated lines. So this is going to be a singular connection between point A and point B in that connection-oriented version where everything follows the same path. For the entire transfer of data, everything's going the same way. So if I wanted to get from my server up in Chicago, wherever that is, down to my computer in Arizona, it would be following the red line exclusively. Packets are always going to follow that. However, if we have packet switching, it breaks the data into packets, and then each one is just given the source and the destination and said, go find your way there. You could follow the red line, you could follow the blue line, you could make your own green line in here. So this is the difference between circuit switching, which is going to be establishing a connection, connection-oriented, TCP, or packet switching, which is connectionless. So it breaks the data into packets. Each packet takes its own route. Each packet is given a sequence number. So when we send all the data across, we could have hundreds of packets, thousands of packets, and each one is given a number. I am number 1, I am number 3, and I'm number 7, and I'm number 2. When they get to the destination address, they package themselves back together. So they're like, okay, you remember kids in a playground where you said, okay, everybody line up. Okay, now line up according to the first letter in your first name. And they all run around in corners trying to figure themselves out who goes here. Well, my name starts with an A and yours starts with a D, so I'm going to go ahead of you, that kind of thing. When they get to their destination, they are going to figure themselves out and organize themselves back in order based on that sequence number. So they'll rebuild themselves. When they get to the destination, they can say, hey, we have frame 1, 2, 3, 4, and 6, but we are missing 5. Could you please send us back 5? Because we didn't get 5. And then it goes back to the server, and the server goes, oh crap, sorry, 5 must have gotten lost. Let's go send 5. And then they send 5's packet, and then they can all be built together. So depending on how long it's taking, as they're building up, they can say, we're still missing 5, we're still missing 5. And then they're like, finally, go ahead and resend 5 because we haven't gotten it yet. The packet switching can be basic Ethernet. It can use frame relay, or it could be that FDDI. See if you can remember what FDDI was. Okay, if any of you have ever looked at ASCII characters, you'll get kind of confused when you look at them and realize that letters don't actually start till 65. And some of you may have asked, so there are 100 or 255 codes, but all we need them for is letters, right? And numbers. So, I mean, we could see the numbers start at, like 50 and go on to the letters that start at like 65 and lowercase letters start at 97. What's the 0 through 50 for? Like, what are those for? Why do we need those? Funny thing is, the first 32 characters in ASCII are all command codes. They are all used to encode something of a command, whether it's the start of the text or the start of the header or the end of the transmission or the start of the transmission or acknowledgement of the transmission, ACK, different types of transmission codes. And we use these a lot back when we were doing encoding that direction. If you needed to encode with standard ASCII characters, how are you going to say it's the start of the header? Well, I'm going to pass a 1, and that's going to be my SOH code, which is my start of header. I'm going to pass a EOT, which is my end of transmission code, which is a 4. And that's what those ASCII codes were for. If you didn't know a lot about ASCII codes before this point, ASCII codes are a standard of 0 to 255 of codes that can be used for plain text with absolutely no formatting. So when we did ASCII codes, it started from 0 and went to 255, and you could encode letters, numbers, punctuation, and obviously command codes. So those were really useful. We found that ASCII didn't cover a huge amount of letters because it didn't get into multiple languages, and it didn't get into hieroglyphics, and it didn't get into a lot of other things. So we increased that to Unicode. Unicode gives you huge amounts of options. You could put little emojis in there. You could put a little mailbox in there and different types of options. There's 16 bits. So instead of the 8 that would go with character code, with an ASCII code. And we actually use these a lot in barcodes, both in barcodes and in Braille. So we can use Unicode to do multiple languages. You've got all those fun little letters in Russian and Latin and Chinese that we don't use in English. English always think they're the only letters in the world, but there are a lot of letters out there that we don't use. So those are all included in Unicode. And then, of course, we have to throw out the HTML. So HTML is technically a markup language. It's to define, so hypertext markup language is what it stands for. And it's designed to allow you to format documents for the internet, obviously websites. In those, we actually give a 6-digit hex code to refer to individual colors. So we have the examples here of all F's is the color white. All zeros is the color black, and everything in the middle is a series of hexadecimal 16-bit numbers. So hexadecimal would be 0 to 9, and then for 10 we use A, for 11 we use B, up to 15, which is F. So that's a hexadecimal number. So when you see FFCC33, those are all hexadecimal numbers used in a hexadecimal 6-digit code to refer to a specific color of orange. So these are different data codes, and you can see how each of those can be encoded. Each character in a hexadecimal number 0 through 15 can take up a certain number of bits. That's how we do that. Instead of saying that we're just going to do decimal doesn't break nicely into binary, but hexadecimal does. So we use a lot of hexadecimals in coding. Okay, so I promised you some detail on frames. These are some examples of a UDP frame and an Ethernet frame. So our UDP, remember UDP is connectionless. It defines the source and the destination port. So you can see source port and destination port given as 16-bit characters or 16-bit numbers. They want to keep track of how long the length is because we want to know how long we have to look. And then they have something similar to a CRC, which is an integrity check that we call checksum. Then we send our data. Again, we don't need to know about responses because we're just dealing with our UDP frames and it's connectionless. So in this case, we have a source port, a destination port. What is the length, the checksum, and the data? And that is your basic UDP frame structure. Over on our Ethernet frame, we have what we call the preamble, which we use for the start of frame. It's 64 bits to say we're starting the frame now. Everybody understands where we are and we know it's going to take up 64 bits. We then have our destination and source addresses. We have the type of Ethernet frame, which is going to be which upper layer is going to guarantee my delivery. And then we have our frame check sequence, which again is similar to our CRC. The frame check sequence actually occurs at the end of the data header. So you have your data in the middle and then your frame check sequence is at the end. So we can use those with our Ethernet 2 frames. We also have included an IEEE 802.3 frame, which also includes that preamble, but it includes this SFD, which is a start frame delineator, which indicates the start of the frame with a single 1-byte binary pattern in the 802.3 frame. Again, destination and source. In the middle, we have length because we'd like to know how long it's going to be, and then our data, and then again, our frame check sequence at the end. So this is the different types of frames. Remember how I said they're going to take that header, that source and destination, they're just going to combine it with a couple other pieces of information. There are two different frames that are also introduced at this point. One is called a broadcast frame. A broadcast frame is being sent to every computer on the network. So I'm on a network, there are 10 computers on it, and my broadcast frame is going to tell the frame structure, I'm sending this to everybody. You also have a multicast where you can pick, I'm going to send it to John and Mary and Joe, and those 3 computers are going to get this. So I've pre-selected a group of computers and I'm multicasting it or sending it to multiple computers all at the same time. So you can have a broadcast frame, you can have a multicast frame, or what normally occurs is a unicast frame, which is to a single computer. 3 different types of frames that you're going to be working with. As I've said multiple times, the OSI model is going to keep coming up. Memorizing this is going to really help you. So let's talk about how data encoding works with the OSI model. A couple of you wrote down for the application layer that it is a user interface. It's not. Please understand, the user interface is like a GUI. It's a thing with windows and buttons. That's not the application layer. It uses the word interfaces, which I understand can confuse a lot of people. Interfaces just means works directly with. So if I were standing in front of you, I would be interfacing with you because I'm talking to you and I'm working with you. It is not a user interface. So our application layer interfaces with the network system. So if you have Microsoft Word and you want to package it up and send it to a friend through the network, Microsoft Word will interface with the application layer to figure out what to do with that file. If you're going to send an email with an SMTP through your browser or through your email client, that email client is going to interface with your application layer. It's going to talk to the application layer and figure out what to do with its email when it sends it. The presentation layer is going to package all the data according to whatever form we've agreed on. And it's going to depend on what situation. Is it a JPEG? Is it an ASCII file? Is it a WAV file? What type of style of presentation do you want this file in? WAV files would be formatted differently. Their sound than an ASCII file, which is just straight text. So we're going to package the data that you want into a way that we know is going to be converted and sent across media. our session layer. This one establishes your session, or your coordinates communication between your 2 points. So you are going to be doing that coordination of how am I going to establish a session if it occurs at this point. Both your TCP, your Transmission Connection Protocol, and your UDP, your User Datagram Protocol, are both at the transport layer. This is where they start coming in, and we are going to frame things differently based on which protocol we're going to use. So transport layer is where we start talking about putting in those protocols to figure out what we're going to do. The network layer adds the IP address for your routing. The network layer encapsulates those packets and attaches that IP address so that it can be routed. If it's inside a local area network, the IP address isn't necessary, but otherwise the IP address exists at this layer. So the TCP and UDP occur at the transport level. IP exists at the network level. Then we go down into the data link level. The data link layer is going to convert your frames and packets into electronic signals and put them on the media. So the MAC layer converts them to electric signals, and the LLC addresses the packet. So your CRC also gets set at this point. So as we're starting with our email up at the top in our application layer, take your email, it's going to go down to the presentation layer. So the email program, your Outlook or whatever, or your Gmail, is going to talk to the application layer, and they're going to say, here's an email. Applications layer, cool, thanks. I'm going to pass you down to the presentation layer. Presentation layer goes, okay, this is an email. I need to format it like this. Cool. Hands it off to the session. The session goes, okay, cool. I need to figure out where it's going and establish and coordinate communication if I need to keep that communication in that session open. Here it goes, give it off to the transport level. TCP or UDP at this point says, okay, cool, I'm in charge. Let's make sure we transport this correctly, get everything set, and then send it down to the network layer. The network layer takes that, packages it for routing, and sends it down to the data link layer, who puts it into frames. So when I said it went from data to segments to packets to frames, that's how we're doing this. So at the transport layer, we're starting to get into segments. Down into networking, we start encapsulating, so taking that segment, breaking it down into packets. Once it's in a packet, we hand it off to the data link layer that puts it into frames. And then finally, we're in a binary situation. We can put it on the media and send it across. This is where the visual of that. Now, when it gets to where it's going, this reverses. It goes the other direction. So the network media hands it up to the data link layer that recognize the frames and being able to put them back into packets, hands the packets up to the network, which starts to break up the packets into segments, which hands it up to the transport, which then takes those segments, put it into raw data, hands it up to the session if we need to keep track of that session, otherwise hands it up to presentation, which is going to go, oh, cool, it's an email. Let's hand it to the email, and hands it up to the application, and the application goes, where's the email client? Oh, there it is. Here's your data. So start from the top, work our way down to physical, then come back up to the application again after it gets where it's going. Hopefully that starts to understand what the different layers are in your OSI model are doing through your transmission process. Okay, so we finished up our media section. We can work in operating systems next chapter. So review questions obviously are optional. You can choose to do those. Go ahead and do your study guide. For your lab activities, you shouldn't need anything excessive except the Wireshark application. You're going to go to wireshark.com and download it if you haven't already done so. There are sample files with Wireshark that are in the content resources folder in D2L. So you'll see those are in there, and you'll see in the labs which sample file they want you to use. Wireshark is this kind of fun little project where this application that you can run on your computer, and you just capture off your network for a very short period of time. Like you could turn on the capture and turn it back off 5 seconds later, and you'll have 20 or 30 different frames that were captured. You can then look at each of those frames, click on them, and see the different layers of the OSI model in order. Usually Wireshark will tell you the frame information at the top at the physical layer, and then it will go down to the Ethernet 2 layer, and then it'll go into layer 3, layer 4, layer 5 as it goes along with the different layers. So it starts with its physical at the top, and then it keeps going down. You'll see when you open it up what it looks like. And it's actually kind of fascinating being able to get in there and actually see your header, see your frame, see the frame broken down. Where is your data? Look at the different things. So the labs for this, all 3 labs are due. All 3 labs are required because you don't need anything extra other than Wireshark and a network connection. There is a study mate for Chapter 5, and don't forget to take the Chapter 5 quiz. In addition, don't forget that discussion for Chapter 5. The discussions are really great. I'm loving the way that those are coming across. So I'm really enjoying all of your comments. So I hope you enjoyed this chapter on data transmissions. If you have any questions, please let me know or put a comment in the chats. Please come back next time for Chapter 6. Have a great day.